Okay, welcome back. We are talking now about the spring force, or Hooke's law. Okay, so let's see. Oh, I don't have it printed here, but the example we did in class was first with the tire gauge. If you remember, it's, okay, so you have this little gauge here. And when the rush of air comes in, it pushes down the spring, which then pops out the little rod that tells you what the tire pressure is. So what's going on here with the free body diagram, if we sum up all of our forces, we have the force of air coming in, and we have the spring force directed upwards. So the sum of all the forces, and let's say that's in the y direction, equals Fs minus the force of air, and we know that equals 0 because it's not moving. So spring force equals, well, actually I'm going to do it the other way. I'll do it this way. Spring force equals the force of air, or written the other way, force of air equals spring force. Well, we can't break down the force of air anymore because that's what the question's asking for. There's no way we can represent the force of the air. We're just told to calculate it from what we're given in the problem. The spring force is equal to negative k delta x. That's Hooke's law. Now, what I should have done from the beginning is draw a sketch of the situation just with a simple spring, where this is x0 and this is x. And the problem gives us the spring constant, 320 newtons per meter, and x0 we just define as 0, and x now is negative 2 centimeters, which is the same as 0.020 meters. Okay, so the force of the air equals negative 320 newtons per meter. I should say this is negative k x final minus x initial, which is 0. So negative 320 newtons per meter is k, and x final is negative 0.020 meters. So the force of the air just equals 6.40 newtons. Newton per meter times meter is newtons. Now keep in mind, we're talking about magnitudes here. That is why this comes up to be positive instead of negative, because the magnitude of the spring force minus the magnitude of the air is 0. If we wanted to talk about this in vector form, plus force of air. So we're just adding vectors. That's all we're doing. But when we plug in, the negative k delta x, where x is now the displacement vector, then that negative is going to show up. And so you're going to get a negative answer indicating that the force is downward. But I suggest not dealing with the vectors and just dealing with magnitudes. So we know at the end here we have a positive number. That just means that we assumed correctly and the force is downward. If we were to end up with a negative number, then we would have assumed the wrong thing, and we would have to reverse the force. Okay, so now here's an example I have on the sheet. Spring constant of a spring is 320 Newton per meter, and the bar indicator extends 2 meters. Oh, well, that's the one we just did. I did put that on there. So next we have a 13.2 kilogram mass that's placed on top of a vertical spring, and the spring compresses by that amount. Find the force constant of the spring. So this is the relaxed length of the spring. And now we have this mass, x0, x1. And we know that k, no, know we don't know K. That's what we're looking for. But we know mass equals 13.2 kilograms. And we know x1 equals 0.0593 meters. I just converted this from centimeters to meters by moving the decimal place to 2 places. x0 equals 0. Okay, so just like before, we have a free body diagram, force of gravity times the spring force. So the summation of the forces is spring constant minus the force of gravity. That equals 0. We're talking about magnitudes here. That's it. So the spring constant equals the force of gravity. Now we can expand both of those. Negative k delta x is the spring force, and the force of gravity equals mass m times g. Unless I tell you otherwise, you're on the Earth's surface, so you can just use m times g. You will be told if you're not on the Earth's surface or if you need to bust out Newton's universal law of gravitation. But right now, we can just use mg. And we have to use mg because we're given the mass, not the weight. We're after k, so k equals mg over negative delta x, or it equals mg over negative x final minus x initial. We know x initial is 0, and we know then k equals mg over negative xf, x final. Well, now we can put in our numbers. 13.2 kilograms times 9.8 meters per second squared over negative, what is x final, x1, excuse me, is 0.0593 meters. Once that is calculated out, I'm sorry, that's negative, excuse me, because we're going below x0. So once that is calculated out, k then equals 2.18 times 10 to the third kilograms per, Newton meters. So kilograms, meters per second squared, that's newtons, divided by meters. So your units are Newton meters. Okay, this next one is the beast that was probably pretty difficult. So we'll work through it rather slowly and hope it makes sense to you. The situation is one such that we have, let me draw it this way. We have an unstretched spring. We have a string with M1 attached to it, and we have, okay, I made this drawing way too big. Let me just go back for neatness here. Make the drawing a little smaller. Let's assume it's a small spring. So this is the relaxed state. Then we attach a mass to it, call that M1. So this is x0, this is x1. And once we attach another mass to it, that length triples. M1, M2, and this is x2, but this equals 3 times x1 minus x0. I'm sorry, I think today you said you preferred to use y because we're in the y direction, so let me just change that. It doesn't matter, but if it makes a little more sense conceptually to you, we'll do that. Okay, So the problem says the amount that the string stretches from its unstrained length triples. So this is the amount that it stretches from its unstrained length. That then triples. So y1 minus y0. Now at y2, we're at 3 y1 minus y0. So I'm going to look at two situations. Situation 1 that deals with the one mass, and situation 2 dealing with both masses. So with situation 1, we have Fg1 equals the spring force. Summing them up, Fs minus Fg1 equals 0. Well, to be more explicit, it equals mass times acceleration, and there is no acceleration, so it equals 0. So Fs equals Fg1. The force of the spring is equal to negative k delta y delta y1, which then equals Fg1, which is just m1g. So I just expanded those two. So negative k times y1 minus y0 equals m1g. And why don't we just go ahead and define y0 as 0, and I'll write down what I know about this stuff. Mass 1 equals 0.70 kilograms, and y0 equals 0. M2 equals, we don't know, where to find that. I just wrote down what we knew about the problem. Okay, so I'll take y0 out because it equals 0, so negative k y1 equals m1g. Not much else we can do with that. I'll call that equation 1, and we'll just circle it and hold on to it. So with situation 2, same kind of situation. We have the force constant, and now the force of gravity is Fg1, 2. It's Fg1 and 2. So summing the forces in the y direction equals Fs minus Fg1, 2, and we know that sums to 0. Well, again, to be explicit, it equals mass times acceleration, and acceleration equals 0, so that sums to 0. So Fs equals Fg1, 2. So let's expand Fs again. Actually, I should say that's Fs2, because it's a different spring force, because it's a different scenario. So it's negative k delta y2. That's the delta, that's y2, delta y2 would be y2 minus y0. Fg12 equals mg, but now it's m1 plus m2g because the masses are together. So then, this distance, delta y2, is equal to 3, excuse me, times y1 minus y0, because we defined that up here, 3 times the stretched length here, equals m1 plus m2g. We know y0 equals 0. We said that before. So negative k times 3y1 equals m1 plus m2g. Or negative 3 times k y1 equals m1 plus m2g. Now what do we do here? Actually, I'm going to leave the negative sign inside. You'll see why in a moment. Well, let me go ahead and take it one more step. Negative ky1 equals m1 plus m2 over 3 times g. So you'll notice we have a negative ky1 here, and we have a negative ky1 here. I'm just going to take this down and insert it. So that means m1g equals m1 plus m2 over g over 3 times g. All I did was that I know negative ky1 equals m1g. I solved that up here. Then I inserted that here for negative ky1. All right, so g's cancel out. And now it's just a matter of solving for m2. Multiply each side by 3. So 3m1 equals m1 plus m2. Subtract m1 from each side. So we have 2m1 equals m2. And therefore m2 equals 2 times 0.70 kilograms, or m2 equals 1.40 kilograms. Whoops, that's our answer. Okay, looks like my problems may be a little out of order here. Because we have a car suspension. Yeah. So now we're going back to a little bit easier problem. I think these got out of order somewhat. So a car drops 1.2 centimeters when an 80 kilogram person gets in. What is the constant of this suspension system? All right, so I'll say x0. This is the spring normally, and when it's compressed, x1 equals negative 0.0120 meters. And we know mass equals 80.0 kilograms. So what is the spring constant of the system? Well, if we draw the free body diagram, don't skip these steps, because I know this seems obvious to some of you after a while, just drawing, okay, FG and FS. But we're going to have situations where this is not the case. So always draw this out. Like, let's say you have a block on an inclined plane attached to a spring. Well, now you've got a completely different situation. You have FG, you have the normal force, you have the force of the spring, you know, this is theta, that's theta. Okay, so everything gets super complicated. Well, just get in the habit of always drawing a free body diagram, so that way you visualize all the forces acting on the system. So summing up the forces in the y direction, we have Fs minus Fg equals Ma, which equals 0. So Fs equals Fg, negative K delta X equals Mg, Fg equals Mg. So negative K X final minus X initial equals mg. X0 is just 0. I'm sorry, it's just x1, not x final. So negative k x1 equals mg, and k equals mg over negative x1. Or k equals 80.0 kilograms times 9.8 meters per second squared over negative 0.0120 meters. And that equals 6.53 times 10 to the 4th Newton meters. Okay, this last one is a bit of a doozy. You have a 7 kilogram block that's pulled some distance on a frictionless horizontal surface starting from rest, and it takes 7.75 seconds. The block has a constant acceleration and is pulled by means of a horizontal spring that is attached to the block. The spring constant is that, 415 newtons per meter. By how much does the spring stretch? Alrighty. We need to write down everything we have. T equals 0.750 seconds. Mass equals 7.00 kilograms. X0 equals 0. X final equals 4.00 meters. Starting from rest, so V0, we'll say V0x if you want. It's all in the x direction, so that equals 0. Vx, we don't know what that is. And we have the spring constant equals 415 Newton per meter. By how much does the spring stretch? So, okay, we're talking about two very different situations here. I'm going to say D equals the stretch of spring. We don't know what that is, and we want to find it out. Now, the reason I'm using D here instead of X is because we're already employing X over here. We have two different distances that we're trying to measure. So if I draw a picture, I have, this is D, no, not D. Well, we could say D0 if you want to say that. And at this point, we have FG, FN, and that's it. At some point in the future, this is where the block was at one time. Now it's here. And so I can say D0. I'll call this D. That is, oops, nope. So D is going to be the amount it's stretched. Or if you want to call it delta D equals D minus D0, that's fine too, whatever. But this is going to be X0, and this is going to be X. So that is the distance traveled by the block. If I draw a free body diagram in this situation, we know we have an acceleration, so that spring force is going to apply, is going to be applying that acceleration. We know that Fg equals Fn in magnitude. Okay. These two, well, if we sum up our forces in the x direction equals Fn minus Fg, and we know that equals 0. So there's no acceleration in the y plane. And the sum of the forces in the x direction equals the spring force. That's it. But we know that is not equal to 0. So sum of the forces in the x direction equals the spring force equals mass times the acceleration in the x direction, because the block is accelerating. And we can further say negative k delta d if you want to. Let's just call it d. D is the stretched length, equals max, or k equals max over negative d. So we have an expression here for the spring constant k. All we need to do is find that acceleration with which the block is, with which it is accelerating. So from there, we can just use your basic kinematics, correct? So if you remember that one kinematics equation, x minus x0 equals v0 xt plus 1/2 at squared. Is it? Do we? Yeah, we do have t. So in this case, x0 we said equals 0. v0 is starting from rest, so that equals 0. So then x just equals 1/2 a, I guess it'd be ax t squared. Okay, we have t, we have x, we don't have acceleration. So 2x equals ax t squared, or 2x over t squared equals ax. Well, now we can just oh, I'm so sorry. The problem asks us to solve for the distance, not k. D equals negative k. Okay, problem solved. So now d is just equal to m times 2x over t squared over negative k. So d then is equal to mass, which is 7.00 kilograms, times 2 times x, which is, well, 2 times 4.00 meters, over t squared, 0.750 seconds, all over negative 415 newtons per meter. Oops, sorry. So then d, once you calculate that out, equals negative 0.240 meters. The negative meaning, of course, because it's just stretching towards the left. Because you're pulling this way, but the stretching is towards the left. Obviously, because d here is going to be smaller than d0. Yeah. Okay. And that is all the examples for Hooke's law and gravitation.